Tonight, we are going to talk about what happens after humanity reaches Mars. Because the first human landing on the Red Planet will not be the end of the story. It will be the beginning of a much larger one. Mars will not become a second Earth overnight. It will be cold, dry, dangerous, and far from home. Every breath, every drop of water, every kilogram of food, and every return trip will have to be planned with extreme care. But if humans can learn to survive there, build there, and use the resources of another world, Mars could become the first true stepping stone into the rest of the solar system. After Mars, the question changes. It is no longer only whether humans can visit another planet. It becomes whether humans can become a species that lives beyond Earth. Before we begin tonight's journey, subscribe to the channel if you want more calm space documentaries like this. Leave a like if you enjoy slow journeys through the future of space exploration. And write in the comments where you are watching from and what time it is where you are right now. It is strange to think that people are listening from different parts of one small planet, while the future of humanity may one day stretch far beyond it. Tonight, you are watching the Space for Sleep channel, talking about what comes after humans reach Mars. The first thing to understand is that reaching Mars is not the same as mastering Mars. A human landing on the Red Planet would be one of the greatest moments in history. It would be compared to the first steps on the Moon, and in some ways, it would be even more difficult. The crew would not be a few days from home. They would be months away. Their planet would appear as a bright point in the sky. Every delay, every failure, every small mistake would happen in a place where rescue is not waiting nearby. But even that first landing would not mean Mars had been conquered. It would mean humans had touched it. Can we go back? Can we stay longer? Can we survive the second mission, the third mission, the 10th mission? Can Mars become a place humans work, build, repair, grow food, make fuel, and return from without depending on every single kilogram being sent from Earth? That is what comes after humans reach Mars. Not a giant leap to Jupiter, not instant cities under glass domes, not a quick transformation of a dead desert into a second Earth. The first future after Mars is repetition. The first mission can be built around survival and return. Every piece can be planned for one crew, one landing zone, one window, one mission timeline. But a long-term future requires more. It requires cargo before people. It requires backup systems before emergencies. It requires spare parts, power, communications, landing pads, radiation protection, surface mobility, medical planning, and a way to leave again. This is where the meaning of success changes. On the first landing, success may mean the crew touches the surface, completes the planned work, and returns alive. After that, success becomes broader. It means the next crew arrives to find useful equipment still working. It means power systems survive between missions. It means cargo lands close enough to be used. It means the surface is no longer a blank place. Every mission must start from zero. Mars will not reward confidence. It will punish assumptions. Mars is not a cold version of Earth. It is a hostile planet with a thin CO2 atmosphere, low pressure, extreme cold, global dust, no breathable air, and radiation exposure that Earth's magnetic field and thick atmosphere normally protect us from. A person standing outside without a pressure suit would not be exploring. They would be dying. So the first lesson after Mars is humility. The planet is close enough to dream about, but not close enough to forgive us. It is Earth-like only in the broadest visual sense. It has a day length similar to Earth's. It has seasons. It has ice. It has ancient evidence of water. It has ground to land on. Compared with Venus, Jupiter, or the outer moons, Mars feels almost welcoming. But almost welcoming is not the same as safe. That is why reaching Mars cannot be the final goal. The landing is only the first proof that a human body can be delivered to the surface. The next proof is whether human life can be protected there for weeks, months, and eventually years. The first crews would likely live inside machines, pressurized habitats, spacesuits, rovers, life support systems, radiation shelters, airlocks, storage modules, and power units. Their world would not be the open Martian landscape. Their world would be the small bubble of Earth-like conditions they brought with them or built around themselves. Outside that bubble, Mars would remain Mars, beautiful, silent, dry, freezing, and deadly. That is why the first question after Mars is not where do humans go next? It is, how do humans stop Mars from being only a place they visit? A visit is temporary by definition. A visit depends on leaving. A real future on Mars depends on returning often enough and staying long enough for infrastructure to build upon itself. The first mission would have to leave behind more than footprints. It would need to leave knowledge, equipment, tested systems, safe landing data, and perhaps supplies for the next crew. This is why the idea of Mars as a finish line is misleading. It turns the planet into a trophy, something humanity can claim and then move on from. But Mars is not a trophy. It is an environment. And environments do not care about symbolism. They care about pressure, temperature, radiation, chemistry, distance, and failure modes. That accumulation is everything. The early missions would teach what no simulation can fully answer. How does Martian dust behave when humans bring it into airlocks every day? How do suits wear down after repeated surface walks? How do people sleep under a different sky, with Earth far away and communication delayed? How does equipment handle months of cold, dust, radiation, and mechanical stress? How do crews repair something when the replacement part is not coming for months? These are the questions that decide whether Mars becomes usable. They are not as dramatic as the first footprint, but they matter more for the future. A loose seal, a jammed hatch, a battery losing capacity, or dust getting into a joint may shape the next generation of designs. Mars will turn engineering into experience. The future after Mars will not begin with skyline shots. It will begin with checklists. On the first mission, every major system is precious. In a settlement, every major system needs a backup. Then the backup needs a backup. Air, water, power, heat, food, communications, navigation, medical support, and return capability cannot depend on one fragile chain. Earth is filled with redundancy we barely notice. If one farm fails, food comes from another. If one power line goes down, grids can reroute. If one vehicle breaks, another can arrive. Mars begins without that web. Everything has to be brought, built, or invented. That is why a Martian base would probably grow slowly. First, a landing site becomes known. Then, equipment is placed there. Then, power and communication systems are tested. Then, more cargo arrives. Then, the next crew uses what the first crew left behind. A base is not born in one landing. It is layered into existence. That is why the first Martian base would not feel like science fiction. It would feel like an industrial survival camp on another planet. That is why Mars will change our definition of exploration. On Earth, exploration often meant entering a dangerous place with the possibility of returning to a larger safe world nearby. On Mars, the safe world is the small habitat. The dangerous place is everything outside it. The explorers would not move into the unknown from a secure civilization. They would carry the secure civilization in miniature. The return trip matters more than people sometimes admit. A one-way dream is easier to imagine than a responsible mission. But a sustainable human future requires return, rescue, rotation, and choice. People must be able to go home. Crews must be replaced. Equipment must be upgraded. Medical emergencies must have plans. Mars cannot become a prison and still be called a healthy future. So after humans reach Mars, the next achievement is not only staying, it is making Mars part of a route. This is why Mars is not the end of exploration. It is the first planet where humanity has to learn the difference between arrival and presence. Arrival is a moment. Presence is a system. Arrival is a photo. Presence is a supply chain. Arrival is a cheer from Earth. Presence is a crew waking up on Sol 180 and still having power, air, water, food, and work to do. That difference may define the entire future. If humans only arrive, Mars remains a destination. If humans create presence, Mars becomes a platform. A destination ends with the landing. A platform begins with it. From that platform, later missions can become longer, safer, and more ambitious, because each one does not have to carry the whole future alone. Mars is close in the scale of the solar system, but far in the scale of human life. A message can take minutes to travel one way, depending on the positions of Earth and Mars. Real-time control from Earth becomes impossible. The crew must be able to act without waiting for instructions. Robots on Mars may need more autonomy. Base systems may need to diagnose problems before Earth can respond. This delay changes the relationship between Earth and the crew. Earth can advise, calculate, plan, and support. But it cannot hold the crew's hand through every emergency. A leak, a fire, a medical problem, or a power failure may need decisions before a full conversation with mission control is even possible. Mars forces independence before it grants comfort. Mars will test the mind as much as the machine. The crew will live in confined spaces with limited privacy, high stakes, delayed contact, and a landscape that is both magnificent and unreachable without a suit. The first footprints may feel triumphant. The 100th day may feel different. The real story is not only the landing, but the routine after the landing. Can humans make the alien ordinary enough to survive? A place becomes real when it has routines. A routine means the planet has entered human life. Someone checks pressure levels before breakfast. Someone cleans dust from a suit connection. Someone drives a rover to inspect a power cable. Someone repairs a valve. Someone records the weather and plans the next surface walk. These small actions are what turn a spectacular landing site into a working place. The first Mars landing would be history. The first Martian routine would be civilization beginning to stretch. And that is the bridge to the next step. Before Mars can become a stepping stone to its moons, to asteroids, or to the outer solar system, it must become survivable. Before humans can ask what comes after Mars, they must answer what it takes to stay alive on Mars. That answer begins with the first real Martian base. Not a city, not a dream under glass. A small, pressurized, shielded, practical foothold on a planet that will not forgive mistakes. That answer begins with the first real Martian base. Not a city, not a dream under glass. A small, pressurized, shielded, practical foothold on a planet that will not forgive mistakes. The first base on Mars would probably look nothing like the clean, futuristic cities people imagine. It would not begin with towers, parks, open streets, or children running under transparent domes. It would begin with modules, cables, cargo landers, power systems, rovers, storage containers, antennae, airlocks, and dust-covered equipment arranged around a landing zone chosen for survival more than beauty. The goal would be simple in words and extremely difficult in practice. Keep people alive. Outside the walls, the air is too thin to breathe. The pressure is far too low for an unprotected human body. The cold can be brutal. Dust can cling to equipment and seals. Radiation arrives more easily than it does on Earth. And unlike a research station in Antarctica, There is no aircraft that can arrive quickly if something goes wrong. So the first Martian base would be less like a town and more like a spacecraft that happens to sit on the ground. That is the right way to think about it. A Mars habitat is not just a building, it is a life support machine. If a normal building loses power, people may be uncomfortable. If a Martian habitat loses power at the wrong time, the problem can become life-threatening. If a normal door leaks air on Earth, nobody notices. If a hatch or seal leaks on Mars, the base is losing part of its atmosphere. The early base might arrive in pieces before the crew. Cargo missions could land habitats, supplies, power systems, rovers, and ascent equipment ahead of time. Some of those systems would need to be checked remotely before humans ever leave Earth. If the crew arrives and discovers that the return vehicle cannot work, or the habitat is damaged, or the power system is not ready, the mission could fail before the first week begins. That also means choosing the first base location would be one of the most important decisions of the entire Mars era. The best place is not simply the most beautiful valley or the most dramatic canyon. It has to balance engineering and science. It needs terrain flat enough for landing and surface travel, enough sunlight or access for power systems, possible access to useful resources, safe communication geometry, and scientific value worth the risk of sending humans there. A landing site is the first address of another planet. Choose badly, and every mission becomes harder. Choose well, and the site can grow from a temporary camp into a repeated destination. So a Martian base starts before humans step inside it. It begins with cargo on the surface, waiting. That cargo has to land safely. And landing heavy payloads on Mars is one of the hard problems. Mars has enough atmosphere to create heating and drag, but not enough to make landing easy like on Earth. Parachutes help, but they are not enough for very heavy human-class cargo. Rockets, heat shields, navigation systems, and precision landing all have to work together. The base depends on the landing system before it depends on the habitat. If cargo lands too far apart, the crew may not be able to connect it. If it lands on dangerous terrain, it may be useless. If dust covers key systems, they may lose efficiency. If the landing damages the ground around future pads, later missions may face new hazards. A long-term base needs a controlled arrival zone, not just a lucky touchdown. Power is the heart of the base. Without power, pumps stop, heat systems fail, communications weaken, batteries drain, rovers sit still, water processing stops, and air recycling becomes dangerous. The entire base becomes a countdown. Solar power may be useful on Mars, but it comes with problems. Mars is farther from the sun than Earth, so sunlight is weaker. Dust can settle on panels. Dust storms can reduce light for long periods. Night arrives every sol. Energy must be stored. Panels must be cleaned or designed to tolerate dust. A base relying only on sunlight has to treat dust and darkness as serious threats. Nuclear power could provide steadier energy. A compact fission system would not care about night or dust storms in the same way. It could provide reliable baseline power for life support, heating, communications, and science. But nuclear systems also bring engineering, launch, safety, political, and operational challenges. The future Martian base may use a mix of sources, because one source alone creates vulnerability. Then, there is radiation. On Earth, the atmosphere and magnetic field protect life from much of the harmful radiation coming from space. Mars does not offer the same protection. A long stay on the surface means exposure to galactic cosmic rays and solar particle events. The risk is not a dramatic movie beam. It is cumulative damage, increased cancer risk, possible effects on the nervous system, and danger during intense solar storms. Dust would be another constant enemy. Martian dust is fine, dry, and persistent. It can coat solar panels, cling to suits, enter mechanical joints, scratch surfaces, contaminate seals, and become a health concern if it enters the habitat. Every surface operation brings the risk of bringing the outside world inside. Water is just as important. Humans need water to drink, grow food, clean, cool systems, and produce oxygen. At first, much of it may be brought from Earth or delivered ahead of time. But water is heavy, and a base that cannot conserve it carefully will always be fragile. Recycling would be essential. Wastewater, humidity, urine, and other sources would need to be processed and reused as much as possible. The base would have to become a closed loop. Not perfectly closed, but closed enough to reduce dependence on constant resupply. Food would begin as stored supplies, but long-term presence requires growth. Early greenhouses would not be huge open farms. They would be controlled biological machines. Light, temperature, humidity, nutrients, water, carbon dioxide, plant health, and contamination would all have to be managed. Growing food on Mars is not simply putting seeds in Martian soil. So food production would begin carefully. Hydroponics, aeroponics, controlled growth chambers, recycling nutrients, testing crops, learning which plants give the most value for the least mass, water, and energy. This is why crew selection would be intense. The first people to live in a Martian base would need technical skill, emotional stability, medical training, teamwork, discipline, and the ability to solve problems without panic. They would not be passengers. Everyone would be part of keeping the base alive. Communication with Earth would help, but it would not remove independence. Signals take minutes one way, and sometimes Mars and Earth are positioned in ways that make communication more difficult. The crew cannot rely on real-time instructions. They need procedures, autonomy, and the authority to act. The base would need local maps, local weather monitoring, local navigation aids, and software that helps crews make decisions without waiting for Earth. Mission control would still be essential, but Mars crews would live with a different kind of responsibility. They would be close enough to talk to Earth, but too far away for Earth to steer every moment. Exercise would be essential. Mars' gravity is only about 38% of Earth's. We do not yet know exactly how the human body responds to years in that gravity. It is more than the Moon, less than Earth, and biologically uncertain. Muscles, bones, circulation, balance, and development over long periods all become questions. The first base would be an experiment in human adaptation, whether anyone wants it to be or not. The base would also need mobility. Humans cannot explore or work only a few meters from the habitat forever. Pressurized rovers could allow longer trips without wearing suits the entire time. Robots could scout routes, carry cargo, inspect equipment, and enter places too risky for humans. That is important, because outside work will always be costly. Every extravehicular activity requires suit preparation, oxygen, power, communication, dust procedures, physical effort, and emergency planning. A simple repair outside may take hours. The environment turns labor into a mission. This is the unromantic foundation of the entire future. A base that works for 30 days is impressive. A base that works for 500 days is a different achievement. It means materials, routines, machines, and people have survived not just the landing, but the grind. The future will be built less by heroic moments than by systems that keep working after everyone stops cheering. Before Mars can become a stepping stone to Phobos, Deimos, asteroids, or the outer solar system, it has to become a place where a crew can wake up safely again and again. A base is a promise of tomorrow, not a guarantee, but a system designed to make tomorrow possible. And as that base grows, the question begins to change. At first, everything comes from Earth. The air system, the food, the tools, the fuel, The machines, the spare parts, the suits, the habitat walls, the cables, the computers, the medical supplies, and the first drops of water may all be sent across space. That can work for a mission. It cannot work forever. A permanent future needs Mars to contribute. The planet cannot remain only a destination that consumes supplies. It must become a source of them. The base cannot only land on Mars, it has to learn how to use Mars. That is the moment when the next stage begins. It proves that presence is possible, but it also reveals the limit of bringing everything from Earth. The base can begin as imported survival, but it cannot mature until Mars itself becomes part of the supply chain. The first Martian base keeps humans alive. The next challenge is learning to live off another world. It proves that presence is possible, but it also reveals the limit of bringing everything from Earth. The base can begin as imported survival, but it cannot mature until Mars itself becomes part of the supply chain. The first Martian base keeps humans alive. The next challenge is learning to live off another world. This is the step that changes Mars from a destination into a working place. As long as every breath, every drop of water, every kilogram of fuel, every spare part, and every meal must be launched from Earth, Mars remains fragile. It can be visited. It can be studied. It can even hold crews for a time. But it cannot become a real stepping stone until humans learn to use what is already there. This idea is called in situ resource utilization, or ISRU. It simply means using what is already in place. The first and most important resource may be oxygen. Mars's atmosphere is mostly carbon dioxide. Humans cannot breathe it, but carbon dioxide contains oxygen atoms. With the right technology and enough power, oxygen can be separated from it. This would not make the Martian air breathable outside or terraform the planet, but it could help supply life support and rocket oxidizer. That distinction is important. Making oxygen for a base is not the same as changing a planet. A small machine producing oxygen does not give Mars a breathable atmosphere. It creates a local supply, stored in tanks, protected by valves, monitored by sensors, and used only where humans can control it. The achievement would be practical, not planetary. But practical achievements are what Mars needs first. A tank of oxygen made from Martian air would mean one less tank carried from Earth. It would mean a suit can be refilled, a habitat can be supported, or a rocket system can be prepared. The emotional image of Mars may be a person stepping onto red soil, but the real future may begin when a gauge rises on an oxygen storage tank built on another world. The most important factory on early Mars might not make houses, it might make oxygen. Water is the next key. Water is survival in liquid form. Humans need it to drink, plants need it to grow. Life support systems need it for chemistry and recycling. Water can be split into hydrogen and oxygen. It can be used for radiation shielding, cooling, and fuel production. A base with access to reliable water is in a completely different position from a base that must import every liter. But Martian water is not a lake waiting beside the habitat. It is locked away. This makes water a planning problem. Before it becomes a resource, a base built too far from accessible ice may be forced to import water for much longer. A base built near promising ice may face colder conditions, difficult terrain, or other trade-offs. The first long-term sites will not be chosen for one reason. They will be chosen by balancing many imperfect needs. Some is at the poles, some may be buried as ice under the surface. Some is bound in minerals. Some locations are more promising than others. Finding accessible water ice near a safe landing site could become one of the most important decisions for future Mars planning. Once water is found, it still has to be extracted. That is why living off Mars begins with unglamorous chemistry. Oxygen from carbon dioxide, water from ice, fuel from local resources, nutrients recovered from waste, building materials from regolith. Every useful material made on Mars reduces the chain stretching back to Earth. Fuel production may be the turning point. One common idea is to produce methane and oxygen on Mars. Methane can be made using carbon dioxide from the atmosphere and hydrogen, which may come from water. The exact system would be complex, but the principle is clear. Use Martian CO2 and Martian water to make propellant for the return journey. That matters for the whole future. If Mars can produce fuel, then Mars is no longer only the goal of a trip from Earth. It becomes part of transportation. It becomes a stop in a wider network. Later, missions to Phobos, Deimos, asteroids, or deeper space could use Mars as part of their planning, if the infrastructure grows enough. Fuel also changes psychology. A crew arriving at a base where propellant production is already proven is arriving at a place with a path home. A crew arriving without that assurance is living inside a gamble. The difference is not only engineering, it is trust. At first, the simplest use may be shielding. Move regolith over or around habitats. Pile it into protective walls. Use it to reduce radiation exposure and micrometeorite risk. But regolith is not easy. It may be abrasive, it may be chemically difficult. It may contain perchlorates or other substances that create health and engineering challenges. It can get into seals and joints. It can be dangerous if inhaled. The same material that could protect a habitat could also contaminate it if handled carelessly. So using the ground will require procedures. Robots may gather it before humans arrive. Processing areas may be kept outside living spaces. Equipment may be designed so dusty parts never enter clean zones. The first construction industry on Mars may begin with one simple rule: use the planet without letting the planet poison the habitat. That learning will be slow. Early ISRU systems would probably start small. A demonstration device might produce oxygen. A test drill might extract ice. A small reactor might make a little methane. A robot might move regolith over a test structure. A greenhouse might grow a limited crop. Each success would be measured carefully, because scaling up is the real challenge. This is how Mars would become less alien through repetition. At first, a machine produces a small amount of oxygen and proves the chemistry. Later, a larger system runs for weeks. Then, a backup system is added. Then storage tanks are filled. Then the oxygen is used in a real operation. Each stage turns a dangerous idea into a trusted tool. The same pattern would apply to water. First find it, then reach it, then extract a small amount. Then purify it. Then store it. Then use it in life support. Then use it in fuel production. The most important sentence in early Mars engineering may be simple: do it again. Reliability is repeated success. This leads to a deeper point. Local resources only matter if they create reliability. ISU becomes powerful when the base is large enough, stays long enough, and repeats often enough for local production to pay off. That caution does not make the vision smaller. It makes it possible. The first time a Mars-made oxygen tank is used successfully, the meaning will be enormous. The first time water extracted from the planet supports a crew, Mars will feel different. The first time return fuel is produced on the surface before humans arrive, the entire architecture of Mars exploration changes. Each step would say the same thing: Earth is still home. But Earth is no longer the only place that can support the mission. That is the beginning of a multi-planetary supply chain. Not independence, not a break from Earth. A second source, a second place where survival can be partly manufactured. This is how Mars would teach humans to think differently. On Earth, we often measure value by rarity, beauty, or market price. On Mars, value begins with usefulness. Can it breathe? Can it shield? Can it burn? Can it grow? Can it repair? Can it help the next crew survive? That interconnectedness is the real beginning of settlement. A base stops being a set of machines and becomes an ecosystem of machines, people, biology, chemistry, and local materials. It is not natural in the Earth sense, but it is still an ecosystem. It has flows, air flows, water flows, energy flows, waste flows, data flows. People move through it. Robots maintain it. Mars presses against it from outside. In that ecosystem, nothing is isolated. A greenhouse affects the water system. The water system affects oxygen production. Oxygen production affects storage and safety. Power affects every process. Dust affects power. Maintenance affects trust. Trust affects how far crews are willing to travel from the habitat. The base becomes a chain of dependencies, and the strength of that chain decides how ambitious the next mission can be. This is why resource use is not a side chapter after landing. It is the center of the future. Without local resources, Mars remains a campsite at the end of a very long road. With local resources, it can slowly become a workshop. That is the bridge between survival and settlement. A base that only consumes supplies is always waiting for Earth. A base that produces some of its own essentials begins to gain time. Time allows longer stays. Longer stays allow more construction. More construction allows better resource use. Better resource use allows more ambitious missions. That is the real power of learning to live off another world. It does not instantly create cities. It creates momentum. It turns Mars from a place that drains supplies into a place that can slowly add to them. And momentum matters more than spectacle. A city is too large a word for the beginning. A self-sustaining civilization is even farther away. But a base that makes part of its own air, finds part of its own water, produces some of its own fuel, and builds some of its own shielding, has crossed an invisible line. It is no longer only surviving because Earth sent help. It is surviving partly because Mars has been understood well enough to help. And once that begins, the question after Mars changes again. If humans can make air, water, fuel, shielding, and food in small amounts, the next step is no longer just survival. It is growth. The base can expand. More people can stay. More systems can be connected. Mars can begin to shift from an outpost into something closer to a settlement. Not independent, not easy, not Earth-like, but something new. A place where human life is not just visiting, but beginning to take root inside machines, under shielding, supported partly by the planet beneath it. Not independent, not easy, not Earth-like, but something new. A place where human life is not just visiting, but beginning to take root inside machines, under shielding, supported partly by the planet beneath it. That is the moment when an outpost begins to change into a settlement. Not because it suddenly becomes large, comfortable, or conquered. The change is quieter than that. It happens when the base stops being only a temporary mission site and begins to develop memory. Equipment remains. Lessons remain. Paths are marked. Power lines are extended. Habitats are connected. Storage grows. Repairs become routine. The next crew does not arrive at an empty planet. They arrive at a place where human work has already begun to accumulate. That is what separates an outpost from a settlement. An outpost is a foothold. A settlement is a system that expects tomorrow. The question slowly shifts from, can we survive this mission? To, can this place support the next one better than the last? That is the beginning of permanence. That question changes everything about design. A mission can accept equipment that works once. A settlement needs equipment that can be inspected, repaired, cleaned, modified, and reused. A mission can tolerate narrow margins for a limited time. A settlement needs margins that survive boredom, fatigue, mistakes, and seasons. It is not enough for the first system to function on the day it is installed. It has to become part of a growing place. A real Martian settlement would not begin as a city. It would begin as redundancy, becoming architecture. One habitat becomes two. Two modules become a connected cluster. A storage unit becomes a workshop. A rover garage becomes a maintenance bay. A greenhouse becomes a food experiment, then a food system. A landing site becomes a prepared zone. This is how places become real, not through one dramatic construction moment, but through repeated use. This is why the early population of Mars would likely be small and specialized. It would not begin with ordinary families moving into suburban domes. It would begin with engineers, doctors, biologists, geologists, pilots, technicians, life support specialists, construction crews, robotics operators, and people trained to solve problems under pressure. Everyone would need a reason to be there, because every person adds mass, risk, food demand, water demand, oxygen demand, and medical responsibility. The early base may be fragile, but each layer of infrastructure should make it more resilient. A second power source reduces fear. A second habitat reduces risk. A backup communication system reduces isolation. A larger water reserve buys time. A better workshop turns waiting into repair. A small manufacturing system turns broken parts into solvable problems. This is how settlement slowly replaces rescue. On Earth, a broken system can call on a larger civilization around it. On Mars, the settlement has to become a small version of that larger civilization. It must contain not only living space, but the ability to respond to damage. The more problems it can solve locally, the more real it becomes. Manufacturing may become one of the most important steps after basic survival. At first, it would not mean giant factories. It could mean simple fabrication: brackets, covers, clips, replacement handles, basic tools, seals, panels, structural pieces, custom parts for experiments, and components that can be printed or machined from available materials. Even small manufacturing ability matters when the alternative is waiting months for a delivery from Earth. Robots would likely do much of the early building. They could arrive before humans, unload cargo, inspect sites, move regolith, build berms, prepare landing pads, deploy solar arrays, and assemble simple structures. Humans would guide, repair, improve, and intervene when tasks become too complex. The base also needs to become more closed-loop over time. Every cycle that closes makes the settlement stronger. Water is recovered and reused. Air is filtered and regenerated. Waste becomes feedstock where possible. Plant growth uses carbon dioxide and returns oxygen. Packaging becomes material. Heat is managed instead of wasted. The settlement becomes a web of loops rather than a pile of supplies. This is very different from the way many people imagine colonization. The first settlers are not free because they are far away. They are free only to the extent that their loops work. If water recovery drops, freedom shrinks. If food production fails, freedom shrinks. If replacement filters run out, freedom shrinks. Independence is not a political slogan at the beginning. It is a technical condition. Food production would be one of the clearest signs that Mars is becoming more than an outpost. Stored meals can support missions, but gardens and growth chambers support permanence. Early food systems would probably be small, efficient, and carefully controlled. They may focus on crops that grow quickly, use water efficiently, provide vitamins, and support crew health. But food is not only nutrition. As the settlement grows, social structure would begin to matter. Early crews can operate like missions, with clear command, schedules, and procedures. A settlement is different. It lasts longer. People form routines, conflicts, friendships, habits, responsibilities, and expectations. Governance may begin as mission rules, but eventually questions appear that no checklist can fully answer. Even time itself would feel organized differently. People would live by souls, not ordinary Earth days. Work schedules would follow the needs of the base, the weather, the power supply, and communication windows with Earth. Birthdays, holidays, mission anniversaries, and the memory of first arrivals may begin to shape a calendar that belongs partly to Mars. Who decides how resources are used? Who has authority during an emergency? How are risks accepted? How are private spaces protected? How are conflicts resolved when nobody can simply leave? How does a settlement balance science, survival, construction, and personal life? A settlement is not only infrastructure, it is attachment. People begin to care about a place because they survive in it, work on it, improve it, and remember what it used to be like. The first settlers may look at an old landing module, the way people on Earth look at an ancient building, not because it is beautiful, but because it marks the beginning. Mars history would start with hardware. Still, the settlement would remain fragile for a long time. The safest growth may be modular. Add one system, test it, add a backup, connect it, watch it through seasons. Then add the next. A habitat cluster becomes reliable when it survives not just installation, but time. Another major step would be surface expansion. At first, most activity would stay close to the habitat. Later, pressurized rovers could support longer trips. Field stations could be placed at scientifically important sites. Communication relays could extend the safe operating area. Emergency shelters could allow crews to travel farther without risking everything on a single vehicle. The settlement would begin to grow, a local map. This is how Mars becomes a platform for science. The first missions would collect samples and study nearby terrain. A settlement could support deeper research. Geologists could travel farther. Drills could operate longer. Instruments could be maintained. Samples could be processed in better labs. Seasonal changes could be watched over years instead of days. The search for past habitability, ancient water, chemistry, climate history, and possible signs of life would become more powerful with human presence. A human presence also changes the pace of discovery. A rover can do extraordinary work, but it moves slowly and waits for commands. A trained scientist on the surface can notice a strange rock, change a plan, collect a sample, compare layers, and make decisions in minutes. The settlement would not replace robots. It would give robots partners who can think and respond on the same planet. Over time, if the settlement grows, daily life may become less mission-like. People may work shifts instead of mission timelines. There may be routine maintenance days, science days, greenhouse days, construction periods, quiet hours, celebrations, emergencies, boredom, frustration, and small moments of beauty. A settlement does not have to be comfortable to become meaningful. It has to be lived in. It has to contain memory, labor, danger, and care. The first long-term Martian community would be built from all of these. Not a city of millions, not a second Earth, but a small human foothold, learning how to last. That may be the most realistic version of the dream. Not a shining city appearing all at once, but a stubborn cluster of habitats that keeps improving. A place where the first generation spends more time maintaining systems than making history. And yet by maintaining those systems, they create the history everyone else will build on. And if it lasts, the next question begins to appear. Because once a settlement can survive more than one mission cycle, it changes the map around it. Mars is no longer just a target from Earth. It becomes the center of a smaller local neighborhood. Above it move two small moons, close enough to matter and strange enough to become the first test of travel beyond the Martian surface. A settlement that can keep people alive, produce some resources, Repair some equipment, grow some food, and support repeated missions is no longer only a destination from Earth. It becomes a base for the space around Mars. The first places to matter would not be Jupiter or Saturn. They would be much closer. Two small moons moving above the Martian sky, Phobos and Deimos. Before humans use Mars as a doorway to the outer solar system, they may first learn to move between Mars and its own tiny companions. Above Mars move two small moons, close enough to matter and strange enough to become the first test of travel beyond the Martian surface. Phobos and Deimos would not look like the next great frontier at first. They are not worlds like Mars. They are not round, bright, Earth-like moons with mountains and seas. They are small, dark, irregular bodies, more like captured fragments than familiar planets. Phobos is the larger and closer one, circling Mars so quickly that it rises and sets in a way no moon on Earth ever does. Deimos is smaller and farther out, moving more quietly around the planet. From the surface of Mars, they would look modest. But after humans learn to survive on Mars, modest may be exactly what matters. The next step after a planet does not have to be another planet. It can be a smaller target that teaches a new kind of movement. Mars would teach humans how to land, endure dust, protect habitats, recycle air and water, and turn local resources into survival. The moons would teach a different lesson: how to operate in the space around a planet once a planet is no longer only a destination. That is a major change in perspective. A civilization that only lands on Mars is still mostly thinking from Earth outward. A civilization that uses Mars's moons begins thinking from Mars outward. The first steps beyond Mars would probably not be giant leaps towards Jupiter or Saturn. They would be shorter, more practical, and much closer to the infrastructure humans have already built. A settlement on Mars would make the nearby moons important because they sit in the same local neighborhood. They are not easy, but they are reachable in a way the outer solar system is not. This is how expansion usually works. Not by jumping to the farthest dream first, by turning the nearest difficult place into the next useful place. Phobos and Deimos could become the first places humans visit after Mars is no longer only a landing site. They might be science targets, staging points, observation posts, fuel storage sites, or training grounds for small body operations. Their origin is still not perfectly settled. They may be captured asteroids, or they may have formed from debris after a large impact on Mars, or from a more complicated early history. Their shapes and surfaces hold clues, and in a future where Mars has a real human base, the moons become much more tempting. They are close enough to imagine. A settlement on the surface would need to connect with orbit anyway. Supplies, crew transfers, return vehicles, satellites, and communication systems all depend on the space around Mars. The moons sit inside that same operational zone. But landing on Phobos or Deimos would not feel like landing on Mars. Their gravity is extremely weak. A human would not walk normally. A careless push could send a person drifting. Tools, dust, rocks, and equipment would behave in unfamiliar ways. Anchoring becomes more important than standing. Even moving around becomes a problem of contact, restraint, and control. They could teach how to attach equipment to loose regolith, drill in weak gravity, collect samples without losing them, move safely when every motion matters, and build a small station that does not rely on weight to hold it down. This is why Phobos and Deimos could become stepping stones not only physically, but technically. Working there would force humans to learn operations that Mars itself cannot teach. Mars has enough gravity to stand, drive, bury habitats, and build more like a planet. The moons would teach the opposite: how to operate where gravity barely helps. A mission there would be less about planting a flag and more about learning restraint. On a small moon, every push matters. Every drill force matters. Every landing leg matters. A spacecraft cannot simply assume the ground will hold it. Astronauts may need tethers, anchors, handholds, and vehicles that behave more like climbing equipment than cars. The whole body would have to learn a new relationship with motion. This would prepare crews for places where there is no normal up and down. Around small bodies, navigation is not the same as walking across a landscape. It is more like working between flying and climbing, always aware that the ground is weak and gravity is almost absent. They might also become observation posts. From Phobos, Mars fills much of the sky. A station there could watch the planet, track weather, monitor dust storms, observe landing sites, relay communications, and support robotic operations on the surface. Deimos, farther out, might offer a wider, calmer perspective of the whole Mars system. A small station near or on Phobos could become a place where spacecraft dock, refuel, store supplies, transfer cargo, or wait for the right mission window. It might not have a large crew. It might be mostly robotic. It might be visited occasionally from Mars orbit or from the surface. But even a modest outpost could make the whole Mars system more flexible. It might also make surface missions safer. If a crew on Mars needs a relay, a backup observation platform, or an orbital storehouse, the moons could become part of the answer. If a cargo ship arrives early, supplies might be stored in orbit or near a moon, instead of immediately landing everything on the surface. If a future mission needs to inspect Mars from above, Phobos or Deimos could offer a useful base for instruments. None of this requires imagining a huge city on a moon. A few carefully placed systems could still change the way the Mars region works. This is the moment when Mars stops being just one point on a map. It becomes a system. This matters for return trips too. A spacecraft leaving Mars might not go straight home in every future architecture. It might rendezvous with an orbital vehicle. Cargo might move between surface and orbit. Fuel might be stored in orbit. Crew might transfer through a station. Phobos and Deimos are valuable partly because they move with Mars. They are local destinations that allow a Mars-based civilization, even a tiny one, to practice leaving the planet without leaving the neighborhood. The first crew watching Phobos cross the Martian sky might see it not only as a moon, but as a reachable place. A dark, uneven body racing above the desert, where future astronauts might anchor themselves, look down, and see Mars itself as the world below. There are also scientific reasons to go. Studying Phobos and Deimos up close could help answer questions about their origin and about the history of Mars. If they are captured asteroids, they may tell us about material from elsewhere in the solar system. If they formed from Martian impact debris, they may preserve evidence of a violent event in Mars's past. Samples from these moons could be extremely valuable. They could also collect material ejected from Mars by ancient impacts. Over long periods, pieces of Mars may have reached the surfaces of its moons. If that is true, samples from Phobos or Deimos might contain tiny records of Mars itself, mixed with the history of the moons. A small, dark moon could therefore become a library of impacts, dust, and ancient collisions. That makes them scientifically richer than they first appear. They are not just rocks beside Mars, they are witnesses. The important point is that Mars's moons offer a step between planetary settlement and deep space expansion. They are close enough to be connected to Mars, strange enough to teach new skills, small enough to be technically challenging, useful enough to become part of a wider system. This is exactly the kind of step that would come after the first Martian settlement. Not a giant leap into the unknown, but a careful expansion of capability. Mars teaches surface survival and settlement. Phobos and Deimos teach low-gravity operations, anchoring, orbital logistics, and movement through the Mars system. Together, they prepare humanity for something larger: asteroids. Because after humans learn to use Mars, and move around its moons. The next logical question is whether the same skills can work on the small worlds beyond Mars. The asteroid belt is not close in the emotional sense. It is still enormous, difficult, and mostly empty. But it is the first region where resources beyond planets become central to the future. The Martian moons may be the practice ground. The asteroid belt may be the industry. That is why the small moons of Mars matter. They turn Mars from a single destination into a local system with multiple places to use, study, and move between. They make the next step smaller than the asteroid belt, but larger than the Martian surface. They are the first test of whether humans can operate from another planet outward. And if that test succeeds, the meaning of Mars changes again. Mars is no longer just the place humans reached after Earth. It becomes the place humans leave from next. That may be the true turning point. A species has not fully expanded beyond its home world when it lands somewhere else. It begins to expand when the new place becomes a starting point. When vehicles launch not only back to Earth, but onward. When crews look at a nearby moon and plan the route. When local resources and local infrastructure make local exploration possible. This is the difference between exploration as a line and exploration as a network. A line goes from Earth to Mars and back again. A network connects Earth, Mars orbit, the surface, the moons, cargo vehicles, relay systems, and eventually small bodies beyond. Once that network exists, each point makes the others more useful. Mars becomes stronger because it has access to orbit. Orbit becomes stronger because it has access to the surface. The moons become stronger because they sit between movement and destination. Then, Mars becomes more than a red planet. It becomes a gateway. The first gateway is small, 2 dark moons in the Martian sky, Phobos and Deimos, and beyond them, scattered through the space between Mars and Jupiter, waits a much larger frontier, the asteroids, where the future of space industry may begin. And beyond them, scattered through the space between Mars and Jupiter, waits a much larger frontier, the asteroids, where the future of space industry may begin. But the asteroid belt is not the place most people imagine. It is not a crowded storm of rocks smashing into each other like a dangerous maze from a movie. The distances are enormous. Most of the belt is empty space. A spacecraft could pass through it and never come close to an asteroid, unless the mission was carefully planned to do so. The danger is not that rocks are everywhere. The difficulty is almost the opposite. The useful places are far apart. Mars is not inside the main asteroid belt, but it is closer to it than Earth in many mission architectures. More importantly, a Mars-based civilization would already need many of the same skills asteroid work requires. Local resource use, robotics, autonomous operations, fuel production, low-gravity experience from Phobos and Deimos, orbital logistics, and long-duration survival away from Earth. Asteroids are valuable for different reasons. Some may contain metals such as iron and nickel. Some may contain carbon-rich material. Some may contain minerals with water bound inside them. Some preserve ancient material from the early solar system, almost like frozen records from the time before planets fully formed. They are not all the same. An asteroid is not just a rock. It is a piece of history, chemistry, and possibility. It may be about using asteroid material in space. Water could become propellant, radiation shielding, and life support. Metals could become structure. Carbon compounds could support chemistry. Regolith could become shielding or construction material. The point is not always to bring resources down to Earth. The point is to stop launching every resource up from Earth. That is the central idea. This is why asteroids matter after Mars. Mars teaches humans how to stop depending on Earth for everything. Asteroids extend that lesson into space itself. The first asteroid operations would almost certainly be robotic. Robots do not need air, food, sleep, or psychological support. They can spend years traveling. They can wait. They can work in places too small, too cold, or too awkward for people. A robot can fail without a rescue mission becoming a human tragedy. So the earliest asteroid industry would probably look like slow, careful machines arriving at selected targets, mapping them, touching them, drilling them, heating material, collecting samples, and testing extraction methods. Asteroids would force engineers to solve a new set of problems. Gravity is weak, so equipment cannot rely on weight. Surfaces may be loose rubble rather than solid rock. Some asteroids may be piles of fragments held together gently by gravity. Others may be denser and more solid. Dust can cling, float, or be thrown away. Digging can push the machine backward. Landing can bounce. Anchoring can fail. A mining vehicle on an asteroid cannot simply behave like a bulldozer on Earth. It may need to hold itself down while it works. It may need harpoons, drills, clamps, nets, tethers, or arms. It may need to process material without scattering it into space. It may need to operate in darkness, extreme temperatures, and long communication delays. It may need to make decisions without waiting for Earth or Mars to answer. The first target would matter. Engineers would not choose an asteroid just because it sounds dramatic. They would consider orbit, composition, size, rotation, surface properties, distance, communication, energy requirements, and mission value. A useful asteroid is not only rich, it is reachable, understandable, and workable. That is why the earliest industrial targets may be chosen for boring reasons. A slow rotation could be more useful than a spectacular shape. A stable orbit could matter more than a famous name. A body with accessible hydrated minerals could be more valuable than one that only sounds rich on paper. The first asteroid industry will probably reward patience, mapping, and careful selection more than heroic risk. Before anything is mined, the asteroid has to be understood. Its surface must be mapped. Its mass and rotation must be measured. Its composition must be tested. Engineers must know whether it is solid, fractured, dusty, metallic, icy, or loosely held together. A bad assumption could ruin the mission before extraction even begins. In that sense, asteroid mining begins as asteroid science. This is why Mars could become important. If Mars has surface infrastructure, orbital fuel depots, and experience producing propellant, it may help support missions that would be harder to launch entirely from Earth. Mars might not be the perfect base for every asteroid mission, but it could become one node in a growing system. Cargo, fuel, robots and crews might move through a network instead of starting every mission from one planet. The asteroid belt also changes the idea of construction. On Earth, buildings are made from materials taken from Earth. In space, if we want large rotating habitats, radiation shields, orbital stations, mirrors, shipyards, fuel depots, or deep space vehicles, it may make little sense to lift all of that mass from the surface of Earth. Asteroid material could one day become the feedstock for structures that never need to enter an atmosphere. That is the real dream of asteroid mining. Not getting rich by dragging metal home. Building things where they are needed. A metal beam made in space does not have to survive launch from Earth. A radiation shield made from asteroid material does not have to be lifted out of a gravity well. A tank filled with water from a small body can protect a crew or be processed into propellant. The value is not only the material itself, it is the fact that the material is already up there. But it is important to stay grounded. Asteroid mining is not guaranteed to become easy or profitable. The engineering is extremely difficult. The economics are uncertain, and the first attempts may fail many times before anything like an industry appears. The first useful products may also be invisible to people on Earth. No one may hold a shiny asteroid medal in their hand. Instead, the success might be a depot quietly filled with water, a habitat shielded by material that never touched Earth, or a robotic tug that moves cargo because its propellant came from a small body. Space industry may become important long before it looks impressive. That fits the pattern after Mars. The most important breakthroughs are not always the most beautiful. Oxygen production, water extraction, fuel storage, anchoring systems, and bulk shielding are not glamorous, but they are the things that make the next mission possible. Mars would help because it creates demand. A growing Mars settlement, orbital stations, and missions through the Mars system would need propellant, shielding, spare material, and construction feedstock. A resource is more valuable when there is someone nearby who can use it. If the only customer is Earth, asteroid material must compete with Earth's massive industrial base. But if the customer is already in space, the logic changes. The asteroid belt could also become a scientific frontier. These bodies are remnants from the formation of the solar system. They can tell us about the materials that built planets, the delivery of water and organics, and the early conditions around the young sun. Industrial interest and scientific interest would overlap, and that overlap would need care. Mining a body that contains priceless scientific information could destroy evidence if done carelessly. Still, if humanity is going to expand beyond planets, asteroids are almost impossible to ignore. Planets are deep gravity wells. Moons are useful but limited. Asteroids are scattered sources of mass across space. They could become supply points, construction sites, research stations, or stepping stones. They could provide the bulk material that makes large-scale space infrastructure possible. It means the solar system becomes less like a set of destinations and more like a geography of resources. Mars provides a surface and a foothold. The moons provide local staging and low-gravity training. Asteroids provide scattered material. Stations provide shelter. Depots provide fuel. Robots provide labor. Crews provide judgment, repair, science, and purpose. The old question was, can humans reach Mars? The new question becomes, can humans build a working system beyond Earth? The asteroid belt may be where that question begins to receive its answer. This is the deeper meaning of space industry after Mars. It is not about replacing Earth. It is not about abandoning planets. It is about creating enough support beyond Earth that missions no longer begin from zero every time. Once resources, depots, stations, robots, and routes exist, the next mission can build on the last one. That is the difference between exploration and infrastructure. Exploration asks whether one mission can succeed. Infrastructure asks whether many missions can become easier because the earlier ones left something useful behind. Asteroids may provide the heavy material that makes that shift possible. The future becomes cumulative. Mars made survival possible. Phobos and Deimos made the local system real. Asteroids could make space itself usable. Not comfortable, not crowded, not easy, but usable in the most practical sense. A place where material can be found, processed, moved, stored, and turned into support for the next journey. And once space becomes usable, the next chapter is no longer about one destination at all. It is about connection. A growing network of bases, depots, machines, cargo routes, habitats, and communication links stretching through the inner solar system. That is when humanity's expansion begins to look less like a series of missions and more like an interplanetary network. That is when humanity's expansion begins to look less like a series of missions and more like an interplanetary network. This may be the real future after Mars. Not one destination replacing another. Not Earth, then Mars, then the asteroid belt, then the outer planets, as if humanity is simply moving down a list. The solar system is too large for that. A lasting future beyond Earth would probably grow as a web of connected places, where each place makes the others more useful. Earth would remain the origin. The Moon could remain a testing ground. Mars could become the first true planetary foothold. Phobos and Deimos could become staging points. Asteroids could provide water, shielding, metals, and bulk material. Stations, depots, robotic factories, and communication relays could connect everything into something very different from exploration as we usually imagine it. A mission is temporary. A network is cumulative. A mission launches, travels, works, and returns. A network stays behind. It leaves equipment in useful orbits. It stores fuel. It marks safe routes. It creates backup options. It places antennas where they are needed. It builds habits, schedules, supply lines, and trust. Each new mission becomes easier because the previous one left something behind that still works. That is the quiet power of infrastructure. Infrastructure is rarely dramatic, but it is what allows the story to continue. In space, the idea would be harder, slower, and more fragile. But the principle remains. A place becomes part of civilization when it is connected. After Mars, the question becomes how to connect worlds separated by millions of kilometers, orbital timing, radiation, and long communication delays. The answer is not one giant spacecraft. It is many smaller systems working together: cargo vehicles, depots, bases, habitats, robots, relays, repair stations, power systems, and manufacturing nodes. Each part may look modest by itself. Together, they create the first interplanetary operating system. The first version would be small. It might begin with Earth, the Moon, and Mars. Cargo leaves Earth. Technology is tested around the Moon. Mars receives supplies. Satellites relay communications. Surface crews use local resources. A depot stores propellant. Robots scout landing sites before humans arrive. At first, this still looks like missions. But slowly, the pattern changes. If a depot remains in orbit and is refilled, it becomes part of the next mission. If a rover on Mars supports multiple crews, it is no longer just mission hardware. If a communication relay serves for years, it becomes a piece of geography. If a station near Mars orbit stores tools, fuel, spare parts, or emergency supplies, then the Mars system begins to have depth. Depth means there is more than one way to survive. A network creates alternatives. If one cargo shipment fails, another can replace part of it later. If a surface system breaks, an orbital storehouse may hold a spare. If a landing zone becomes risky, a second prepared site may exist. If a crew cannot return exactly as planned, another vehicle or depot may change the options. The network does not remove danger, but it gives humans more than one thread to hold. That is what makes space settlement different from space visiting. Visiting depends on a perfect route. Settlement depends on many imperfect routes becoming strong together. Mars would be the first major test of this. A Martian settlement could not remain isolated if it wants to last. It would need orbital support, communication relays, cargo timing, fuel production, storage, and robots operating ahead of humans. It would still need Earth-based manufacturing and perhaps lunar testing. Later, asteroid materials could become part of the same system. Mars would not stand alone. It would become one node in a much larger network, and that network would not be controlled in real time. This is one of the deepest changes after Mars. On Earth, networks often feel instant, but across the solar system, light itself creates delay. Mars may be minutes away by signal. The outer solar system can be hours away. An interplanetary network must be partly autonomous. Robots cannot always wait for a human command. A cargo ship cannot ask Earth about every adjustment. A base cannot pause every emergency until mission control responds. A depot cannot rely on constant human attention. Systems must monitor themselves, diagnose problems, avoid hazards, and keep working during long periods of silence. Autonomy becomes the nervous system of the network. Robots can scout asteroid targets, prepare landing sites, inspect depots, repair solar arrays, unload cargo, and build the first pieces of a place that later humans may enter. This makes the future less like a sudden human invasion and more like a slow preparation. Before a crew arrives, machines are already there. Before a route becomes safe, probes have already mapped it. The network is built in layers. Communication is the first layer. Mars needs orbiters and relays. Asteroid missions need deep space antennas. Crews traveling between worlds need stable links to support vehicles and emergency systems. Communication does not make space safe, but it makes isolation less complete. Navigation is the second layer. Everything is moving. Planets, moons, asteroids, spacecraft. A mature network would need maps, tracking, automated guidance, and shared traffic awareness. Power is the third layer. Surface bases, orbital stations, mining robots, relays, and fuel plants all need energy. Solar power weakens farther from the sun, so storage and nuclear systems may become more important. Propellant is the fourth layer. Fuel depots change the meaning of distance. A spacecraft that can stop, refuel, transfer cargo, wait, and continue has more options than one that must carry everything from Earth. Repair is the fifth layer. Machines in space will break. If every failure requires replacement from Earth, the network stays fragile. If parts can be repaired, reused, printed, or machined locally, the network becomes stronger. The final layer is habitability. Humans need protected spaces, radiation shielding, medical support, food, water, air, privacy, and psychological stability. That is why the first network will probably be mostly robotic, with humans occupying only a few carefully supported points. This is not a failure of the human dream. It is how the dream survives. Humans should go where their presence matters, while machines prepare the way and keep systems alive between visits. As the network grows, the idea of a mission changes. A spacecraft leaving Earth might not be a completely independent expedition. It could become one part of a chain, testing near the Moon, refueling in orbit, carrying cargo to Mars, transferring crew to the surface, and leaving equipment for later vehicles. No single vehicle has to do everything. That is similar to how transportation works on Earth. The power comes from connection. Space will never be as easy as Earth, but networks make difficult movement less difficult. The first interplanetary network would still be slow. Months between Earth and Mars, years for some asteroid missions, long waits for launch windows, delays in communication, and careful cargo planning. Nothing like science fiction where ships move freely every day. But slow is not the same as impossible. A slow network can still be revolutionary if it is reliable. If cargo can be sent predictably, settlements can plan. If fuel can be stored safely, vehicles can be reused. If robots can maintain equipment, human visits become safer. The network becomes a multiplier. Mars alone is one achievement. Mars connected to orbit is more. Mars connected to its moons is more. Mars connected to asteroid resources is more. Earth connected to the Moon, Mars and space-based industry is something else entirely. This is how a spacefaring civilization may actually begin. Not with one giant city on Mars, and not with a sudden leap to another star, but with logistics, the quiet, stubborn art of moving useful things to useful places at the right time. This means standards matter. If docking systems, fuel interfaces, communication protocols, tools, and emergency procedures are compatible, the whole network becomes more useful. A civilization grows faster when its pieces can connect. And still, the network will remain fragile compared with Earth. That should never be forgotten. Earth is not just one node among many. Earth is the only living world humans know, the only full biosphere, the origin of every person who first goes outward. A solar system network does not make Earth less important. It makes Earth more clearly precious. The goal is not to abandon the origin. The goal is to extend what the origin made possible. At first, those lines will be weak. A few stations, a few depots, a few robotic factories, a settlement on Mars, a cargo route that works only during certain windows, and a handful of people far from home. But every durable line changes the map. The solar system becomes less silent, less separate, and less unreachable. And once a network exists, even a small one, new questions appear. Where should the next depot go? Which asteroid becomes useful first? Can people live not only on planets, but in the spaces between them? That last question may be the largest one, because a true solar system network is not only about moving from world to world, it is about making the space between worlds useful. The empty regions become routes, orbits become places, transfer points become important, fuel depots become landmarks, stations become harbors. The darkness between planets becomes part of the map. And when that happens, humanity's relationship with the solar system changes again. The future is no longer only about standing on new ground. It is about living inside a connected architecture of worlds, machines, and paths. Mars begins the transformation, because Mars is the first place where humans may learn to survive on another planet. But the network is what makes that survival part of something larger. Without connection, Mars remains a heroic outpost. With connection, Mars becomes one part of a growing system that can reach farther than any single mission. That is what comes after humans reach Mars. Not one next place, a structure, a web, a slow, fragile, expanding network of support. And once that network reaches beyond Mars and into asteroid space, the next great dream becomes the outer solar system. Not immediately, not easily, but eventually, with enough infrastructure, enough patience, and enough robotic preparation, the icy moons around Jupiter and Saturn begin to move from unreachable worlds into possible future destinations. And once that network reaches beyond Mars and into asteroid space, the next great dream becomes the outer solar system. Not immediately, not easily, but eventually, with enough infrastructure, enough patience, and enough robotic preparation, the icy moons around Jupiter and Saturn begin to move from unreachable worlds into possible future destinations. This is where the future changes scale again. A journey to Mars is already beyond normal human experience, but it still belongs to the nearby part of the solar system. Jupiter and Saturn belong to a different feeling of distance. They are not simply farther points on the same road. They are places where planning must stretch across years, where the sun is smaller, where vehicles must become more like self-contained worlds, and where every weakness in the network becomes more serious. Mars is difficult because it is hostile. The asteroid belt is difficult because it is vast and scattered. But the outer solar system is difficult in a deeper way. It is far from the sun, far from Earth, far from quick help, and far from the kind of warmth that shaped human life. Out there, sunlight is weak. Travel times are long. Communication delays grow. Radiation near Jupiter becomes dangerous. Temperatures fall. Energy becomes harder. Every kilogram of equipment must survive a journey into a region where Earth feels almost impossibly distant. So after Mars, humans would not simply rush outward. Mars may teach humans how to survive on another planet. Asteroids may teach humans how to use material already in space. But the outer solar system would demand a mature network, better propulsion, stronger radiation protection, reliable life support, nuclear power, autonomous repair, deep space habitats, and enough experience that a multi-year mission does not begin from zero. The target would not be Jupiter itself, and it would not be Saturn itself. The giant planets are not worlds humans can land on. They are enormous atmospheres, deep gravity wells, storms, pressure, hydrogen, helium, and environments completely unlike solid planets. The real destinations would be their moons: Europa, Ganymede, Callisto, Enceladus, Titan, and many smaller worlds that may seem quiet until we look closely. Mars asks whether a once wet world became dry and cold, and whether life ever began there. The icy moons ask a different question. Can a world far from the sun still hold liquid water inside? Can tidal heating, chemistry, and buried oceans create environments where life might survive without sunlight? Can the ingredients for biology exist in darkness, under ice, around a giant planet? Europa is one of the clearest examples. From the outside, it is a bright, icy moon orbiting Jupiter. Its surface is cracked, stretched, and marked by long, dark lines. Beneath that ice, scientists think there is a global ocean. If that ocean is in contact with rock below, and if chemical energy is available, Europa becomes one of the most important places in the search for life beyond Earth. But Europa is not an easy human destination. Jupiter's radiation environment is harsh. Electronics, spacecraft, and especially people would need serious protection. A surface base on Europa would be extremely difficult. Even robotic landers face major challenges. Humans may one day study Europa from orbit, from a nearby station or through robotic systems. But the idea of people living directly on its surface would be far beyond early post-Mars exploration. Callisto may be different. It is farther from Jupiter and exposed to much less intense radiation than Europa. It is large, icy, cratered, and ancient. For that reason, some long-term ideas imagine Callisto as a more practical human outpost in the Jupiter system. Not because it is easy, but because it may offer a safer location from which humans and robots could study Jupiter's moons. Callisto is not the most famous ocean world candidate in public imagination, but it may be strategically important. A future crew might not land where the science is most dramatic. They may land where survival is most realistic. Then operate robots at the more dangerous places. This would be similar to using Mars as a base for nearby moons or asteroids. The safest human site and the most interesting scientific site do not have to be the same place. That idea will matter again and again. Humans may live where they can survive. Robots may go where humans should not. Ganymede also matters. It is the largest moon in the solar system, even larger than Mercury, and it has its own magnetic field. It may also hold a deep ocean beneath layers of ice. Its size and complexity make it a world in its own right. But like everything around Jupiter, it belongs to an environment shaped by the giant planet's gravity, magnetosphere, and radiation. The Jupiter system is not one destination. It is an entire miniature solar system. A giant planet, many moons, radiation belts, tidal forces, hidden oceans, and extreme contrasts between scientific promise and operational danger. Saturn's system is even farther, but it contains two of the most fascinating moons ever studied: Enceladus and Titan. Enceladus is small, icy, and almost unbelievable. It sends plumes of water vapor and ice particles into space from its south polar region. Those plumes suggest a subsurface ocean, and because material from inside the moon is escaping into space, a spacecraft may be able to study that ocean without drilling through kilometers of ice. That makes Enceladus one of the most tempting targets for astrobiology. Titan is different again. Titan is Saturn's largest moon, and it has a thick atmosphere. It has lakes and seas of liquid methane and ethane on its surface. It has weather, clouds, dunes, organic chemistry, and a landscape that in some ways feels strangely planet-like, even though it is extremely cold and completely alien. Titan may not offer Earth-like life, but it offers chemistry that could teach us about complexity in environments very different from our own. In some ways, Titan might be one of the more physically forgiving outer moons for equipment because of its thick atmosphere and lower radiation environment compared with Jupiter's inner moons. Flying vehicles could work there in ways that are difficult elsewhere. But for humans, Titan would still be brutally cold, far away, and chemically alien. Its atmosphere is not breathable, its lakes are not water, its sunlight is dim, its surface is not a second Earth. The first human role in the outer solar system may therefore be indirect. People may live in protected stations, perhaps near safer moons, while robots explore the dangerous surfaces. Human judgment could still matter enormously, but human bodies may not need to stand everywhere the science happens. This is the future that makes the most sense. Not humans walking everywhere, but humans building a system that allows intelligence to reach everywhere. Distance changes psychology too. Mars already makes Earth feel far away. Jupiter and Saturn make it feel almost unreachable. Communication delays become longer. Mission durations stretch. Emergency return becomes more difficult. Humans would only go when the network is ready. Mars would be the training ground for that discipline. Every lesson from Mars becomes more important farther out. Recycling water, producing oxygen, repairing machines, managing isolation, using robots, preparing cargo in advance, building redundancy, trusting systems, living with delay. If these lessons are hard on Mars, they become critical near Jupiter and Saturn. Eventually, if infrastructure grows enough, human presence may follow, not as conquerors and not as settlers of every moon, but as caretakers of a wider exploration system. The outer solar system is not a promised land. It is a frontier of knowledge, where hidden oceans may exist under ice, where organic chemistry unfolds in alien cold, and where the meaning of habitability becomes wider than Earth-like surfaces. The outer moons would force humility. If Mars teaches that a nearby planet is not easy, Europa and Titan teach that fascinating does not mean friendly. The deeper we go, the more obvious it becomes that Earth is not ordinary shelter. Earth is extraordinary shelter. Every step outward makes that clearer. That realization does not make exploration smaller. It makes it more mature. The point is not to pretend every world is waiting for us. The point is to learn what each world actually is, and to build the right kind of presence around it. Sometimes that presence is human. Sometimes it is robotic. Sometimes it is only a careful orbiting spacecraft, listening, watching, and sampling from a safe distance. And that may become one of the most important lessons of the entire journey. Mars does not replace Earth. The outer moons do not replace Mars. Asteroids do not replace planets. Each world has a role, and each role depends on the others. Earth gives life and industry. Mars gives the first planetary foothold. The moons of Mars give local movement. Asteroids give material. Stations give connection. The outer moons give science so deep that it may change how we understand habitability itself. That is the shape of the future. After Mars. Not escape. Not replacement. Expansion with memory. Expansion with caution. Expansion that understands the difference between a place we can use, a place we can study, and a place we can live. The icy moons around Jupiter and Saturn may one day become some of the most important scientific destinations in human history. But before humans dream of changing those worlds, or even changing Mars itself, there is a question that cannot be avoided. If we become capable of reaching other worlds, using their resources and building inside them, how much should we change them? That question begins closest to home, with Mars. Because Mars is the first world humans may not only visit, but be tempted to transform. Because Mars is the first world humans may not only visit, but be tempted to transform. At some point after the first landings, after the first base, after the first resource systems, and the first signs of settlement, the question becomes larger than survival. Should humans change Mars? Not just use Mars, study Mars, or build small protected habitats on its surface, but alter the planet itself. Mars is not a sleeping Earth. It is a planet with its own history, its own losses, and its own limits. If humans ever try to change it, they would be attempting one of the largest engineering projects ever imagined, changing the climate and environment of an entire world. Terraforming is the name usually given to that dream. In its simplest form, it means making another planet more Earth-like. For Mars, people often imagine thickening the atmosphere, warming the surface, melting ice, releasing gases, raising pressure, creating liquid water, and eventually making conditions where plants, and maybe one day humans, could survive with less protection. It is a powerful dream, but it is also far beyond anything humans can currently do. The danger is that the word makes the process sound cleaner than it is. Terraforming is not painting a world a new color. It is altering energy balance, atmospheric chemistry, pressure, radiation exposure, water stability, surface conditions, and perhaps biology. Every one of those changes would connect to the others. A planet is not a machine with one switch. That is the first honest point. Terraforming Mars is not a near-future extension of building a base. A base holds air inside walls, shields a small area, recycles water, and creates a controlled environment for a limited number of people. Terraforming would mean changing the planet outside those walls. Mars has problems that are not solved by desire. Its atmosphere is extremely thin compared with Earth's. Most of it is carbon dioxide, but there is not enough pressure for an unprotected human body. The planet is cold. Surface liquid water is unstable under present conditions. Mars lacks a strong global magnetic field like Earth's, so the atmosphere and surface are more exposed to solar wind and radiation. Its lower gravity makes holding a thick atmosphere over geological time more difficult than on Earth. Even if humans could warm Mars, the question would not be solved: where does the thick atmosphere come from? How much carbon dioxide or other greenhouse gas is actually available? How much energy would be required to release it? Would the atmosphere be stable? How would radiation be reduced? How would water be protected? How long would the process take? These are not small details. They are the center of the problem. A common version of the dream imagines releasing carbon dioxide trapped in the poles or soil to warm the planet. But research has suggested that the easily accessible carbon dioxide on Mars may not be enough to create an Earth-like atmosphere or allow humans to walk outside without pressure suits. Even a warmer Mars would not quickly become a breathable Mars. Oxygen would not appear simply because the planet became warmer. A breathable atmosphere would require enormous biological, chemical, and geological transformation. That may sound smaller than terraforming, but it is still extraordinary. A pressurized greenhouse on Mars would be a transformation. An underground settlement would be a transformation. A network of habitats connected by tunnels would be a transformation. The planet does not have to become Earth for human life to reshape parts of it. The real question may be whether humans learn to live in artificial environments rather than making every environment natural. Instead of asking only, can we terraform Mars? We might ask, How much of Mars should we change, and why? Because even small changes matter. So the ethical question begins early. If Mars is lifeless, some people may argue that humans have more freedom to use and transform it. If Mars has past life preserved in rocks, then careless activity could destroy evidence of one of the greatest discoveries in history. If Mars has any present microbial life, even hidden deep underground or in special environments, the question becomes much more serious. Because discovering life on Mars would change everything. It would mean life began at least twice in one solar system, or perhaps moved between worlds through impacts. Either answer would reshape biology, philosophy, and our understanding of the universe. If humans contaminate the evidence before finding it, we may never know what Mars was trying to tell us. Planetary protection is not just bureaucracy. It is the protection of a question. The question is whether life exists beyond Earth. If humans spread Earth microbes everywhere before studying Mars carefully, future scientists may face confusion. Did a detected organism come from Mars or from Earth? Did chemistry belong to ancient Mars or to human contamination? Did a potential habitat remain untouched, or did we change it before we understood it? Some regions may need protection. Some sites may be reserved for science. Some areas may be used for settlement and industry. Some ice deposits may be too valuable for survival to ignore. The future of Mars may require zoning, rules, and choices long before it requires terraforming. That sounds less dramatic than planetary transformation, but it may be more important. Mars is not alive in the way Earth is. It has no forests to cut down, no oceans full of whales, no cities of its own. But absence of visible life does not make it meaningless. It is a planet. It has a history billions of years long. Its rocks record ancient climates, impacts, volcanism, water, atmosphere loss, and perhaps chemistry that came close to life or became life. To erase that record carelessly would be a failure of imagination. If humans one day change Mars on a large scale, it should happen after centuries of learning, not after a few successful landings. It should happen with a deep understanding of the planet's geology, climate, resources, possible biology, and long-term stability. It should not be done because old science fiction promised us red deserts turning green. A world can be inspiring without being available for every human fantasy. Mars can be a home for research, a place for settlement, a source of resources, and a symbol of human reach, without becoming a copy of Earth. In some ways, accepting that may be the more advanced idea. The goal is not always to make every place familiar. Sometimes the goal is to learn how to live with the unfamiliar responsibly. That does not mean the dream has no value. Terraforming is powerful because it forces humans to think on planetary timescales. It asks whether intelligence can become a geological force beyond Earth. It asks whether a dead or dying world could be made more habitable. It asks whether life could spread intentionally, not by accident but by design. Those are enormous questions, but enormous questions require humility. One possible future is that Mars remains mostly wild, while humans live in enclosed settlements. Red deserts outside, green rooms inside, protected science regions, industrial zones near resource deposits, habitats buried under regolith, rovers crossing mapped routes, small farms under pressure, children, if they ever live there, growing up knowing that outside is beautiful but lethal. That future may be less spectacular than terraforming, but more honest. It also matches the first centuries better. A settlement does not need a planet-wide atmosphere to grow. It needs enough safe volume for people to live, work, sleep, repair equipment, grow food, and raise the next mission's chances of success. Every cubic meter of pressurized space is valuable. Every tunnel that connects two habitats is valuable. Every shielded greenhouse is valuable. Small, controlled spaces can matter long before the whole planet changes. Another possible future is gradual environmental modification. Humans might warm small areas, use mirrors or local greenhouse systems, cover craters, build enclosed valleys, and expand pressurized regions until some areas feel almost like outdoor spaces, even though they are still engineered. It will tempt humans because it is close, visible, and almost familiar. It will invite grand plans. It will inspire people to imagine cities, farms, domes, and open skies. Some of those dreams may help push technology forward. But the real measure of maturity may be the ability to dream without lying. Mars is not easy. Mars is not waiting to become Earth. Mars is not a blank canvas. It is a world, and worlds deserve understanding before transformation. That does not make humans enemies of Mars. Humans may one day be part of Mars's story. Our machines may become part of its surface. Our habitats may glow in its night. Our footprints may remain in its dust. Our greenhouses may hold the first leaves ever grown there by design. Our children may one day learn the names of Martian valleys, the way children on Earth learn rivers and mountains. After humans reach Mars, the greatest achievement may not be making Mars look like Earth. It may be learning how to live on Mars without forgetting what Mars is. Mars may become the first place where humanity learns that difference. That lesson may become more important than any single technology. Rockets can take humans to Mars. Habitats can keep them alive. Resource systems can help them stay. But only judgment can decide what should be built, what should be protected, and what should be left alone until we understand it better. And if we learn it well, then Mars will not just be the first step into the solar system. It will be the place where humans begin to understand what it means to become a spacefaring civilization without losing humility. That leads to the final question. If Mars is not the finish line, if settlement is only the beginning, if the moons, asteroids, and outer worlds are all part of a larger future, then what is the real meaning of reaching Mars? Maybe Mars matters most, not because it is the place humans arrive, but because it is the place where humanity learns how to continue. Maybe Mars matters most, not because it is the place humans arrive, but because it is the place where humanity learns how to continue. That is the real meaning of what comes after humans reach Mars. The first landing will be historic, but history is not the same as permanence. A flag can stand in the dust while the planet remains empty. A footprint can last for years while no one returns. A single mission can prove courage, engineering, and ambition. But it cannot by itself make humanity a spacefaring civilization. Mars becomes important when it stops being only a destination. It becomes important when it becomes a beginning. At the start, Mars is a question of arrival. Can humans cross interplanetary space, survive the journey, land safely, work on the surface, and return home? Those are enormous questions. But after the first success, the question changes. Can they do it again? Can they stay longer? Can they keep a base alive? Can they make air, extract water, produce fuel, repair machines, and build routines in a place that was never made for them? This is where Mars becomes more than a milestone. It becomes a test of whether humans can turn exploration into presence. That is why the future after Mars is not one clean leap outward. It is a long chain of learning. First, humans must survive the planet. Then, they must learn to use it. Then, they must build there without pretending it is Earth. Then Mars can become a base for its moons. Asteroids can become sources of material. Stations and depots can form a network. And much later, the outer solar system may become reachable. And through all of it, one lesson keeps returning. The future is not made by reaching a place once. It is made by making return possible. That independence will not mean separation from Earth. Earth will remain the source, the home world, the living planet that made every future mission possible. But Mars will teach humans how to carry a smaller version of Earth outward. Pressure, warmth, air, water, food, medicine, power, memory, culture, and responsibility. Every habitat on Mars would be a fragment of Earth, protected from Mars. Every greenhouse would be a piece of biology held against a lifeless landscape. Every recycled drop of water would show that survival can become a loop. Every kilogram of oxygen made locally would prove that another planet can begin to support the mission. Every successful return launch would say that Mars is not a trap. Space is too harsh for empty inspiration. A beautiful vision cannot hold pressure. It cannot filter air. It cannot stop radiation. It cannot repair a cracked seal. It cannot guide a spacecraft through the correct orbit. Inspiration begins the journey, but systems keep people alive. That is why the most important people in the future may not always be the ones standing in front of cameras. They may be the ones checking valves, writing procedures, repairing machines, monitoring crops, building spare parts, calculating trajectories, and making sure the next crew has a safer path than the last one. This is why the future after Mars may look slow from the outside. People may expect giant cities and dramatic voyages, but the real progress may be measured in quieter milestones. A depot refilled, a habitat reused, a robot repaired, a route proven, a greenhouse stabilized, an oxygen plant made reliable. These are not small things. They are civilization in early form. Civilization is not only crowds and buildings, it is the ability to keep life organized against uncertainty. On Earth, that organization is hidden inside the world around us. Air is everywhere. Water cycles through oceans and clouds. Food grows from living soil. Gravity, atmosphere, and biology do most of the work before technology begins. On Mars, civilization has to be visible. The pipes, filters, walls, cables, tanks, panels, batteries, suits, rovers, seals, farms, and machines are not background details. They are the world people live inside. A Martian settlement would remind humans every day that life is not automatic. It has to be maintained. The more humans learn how hard it is to keep life alive elsewhere, the more extraordinary Earth becomes. Every attempt to live beyond Earth should make Earth look less replaceable, not more. Mars is not a backup Earth in any simple sense. The outer moons are not hidden replacements. Asteroids are not homes waiting to be opened. Earth is the only complete biosphere humans know. A future beyond Earth should not make Earth feel disposable. It should make Earth feel sacred. The farther humans travel, the more obvious that becomes. Mars has beauty, but no breathable forests. Titan has weather, but no warm oceans for us. Europa may have an ocean, but under ice and radiation. Asteroids may hold resources, but not a biosphere. Every place teaches something. None replaces the world that made us. Because the purpose of Mars cannot be escape. Escape is too small an idea. If humans carry the same carelessness outward, then distance alone changes nothing. The deeper purpose is expansion with memory, remembering where we came from, what made life possible, and what responsibility follows when a species can touch other worlds. Mars will not give that wisdom automatically. It will only create the need for it. The first crews may be engineers, scientists, pilots, doctors, and technicians. But eventually Mars becomes a human question. How do people live together when every system is shared? How do they make decisions under pressure? How do they balance growth with caution? How do they protect science while building homes? How do they stay connected to Earth while slowly becoming something new? Can humans be patient enough? Can they be honest about risk? Can they build slowly when the dream asks them to rush? Can they protect what they do not yet understand? Can they accept that not every world is meant to become Earth? Mars will ask all of this. And if humans answer well, Mars may become the first step into something far larger than itself. Answering well will not mean moving perfectly. There will be mistakes. There will be failed missions, broken machines, abandoned plans, and ideas that looked simple from Earth, but collapsed under Martian reality. The measure of maturity will be whether humans learn from those failures without turning reckless or giving up. Mars teaches survival. Its moons teach movement. Asteroids teach resource use. Stations and depots teach connection. The outer moons teach humility and the wider meaning of habitability. Together, they form a story that is not about conquering space, but about learning how to belong in it without misunderstanding it. The early years would be fragile, the first base small, the first farms limited, the first resource plants uncertain, the first crews isolated, the first return trips carefully planned. But if the system survives, grows, and repeats, then something irreversible happens. Human life becomes multiplanetary in practice, not just in imagination. It begins modestly, almost quietly, with a few people and a few machines surviving where nothing human had survived before. But once survival can repeat, imagination changes. The impossible becomes difficult, then difficult becomes planned, and planned becomes part of the future. That does not mean millions of people instantly move to Mars. It does not mean Earth becomes less central. It does not mean the solar system becomes easy. It means that human presence is no longer tied to one surface only. A small branch of civilization has crossed the gap and learned to keep itself alive somewhere else. The future after Mars will be dangerous, expensive, slow, and full of failures. It will depend on machines that must work where no human can easily fix them. It will require cooperation across countries, companies, agencies, cultures, and generations. It will not look like science fiction for a long time. But it may still be one of the greatest transitions in human history, because Mars changes the direction of the question. Before Mars, humanity asks whether it can reach another planet. After Mars, humanity asks whether it can continue from one. That is a different kind of civilization, one that does not only look outward from Earth, but begins to build points of presence beyond it. And in the end, that may be what comes after humans reach Mars. Not a single next destination, but a new relationship with distance itself. Mars becomes the first far place that is not only observed, not only visited, but worked with. From there, the rest of the solar system stops being only a background of lights and becomes a set of possible paths. The first human on Mars will matter, but the first person who returns to Mars may matter even more. The first base that survives between crews may matter more. The first oxygen made from Martian air may matter more. The first return fuel made on Mars may matter more. Because those are the moments that say the journey did not end with arrival. It continued. And that is the heart of this entire question. What comes after humans reach Mars? Learning to stay, learning to return, learning to build, learning to use resources without wasting worlds, learning to connect one place to another, learning that Earth is still precious, learning that becoming spacefaring is not one triumph, but a responsibility that grows with every new capability. Mars is only the beginning, not because it is simple, but because it is hard enough to teach us what the beginning really means. Thank you for watching this journey into the future after Mars. If you enjoyed it, leave a like, subscribe for more calm space documentaries, and write in the comments what you think should come after humans reach Mars. A permanent base, Phobos and Deimos, asteroid resources, the icy moons, or something even farther away. Wherever you are watching from, and whatever time it is there right now, remember that all of this still begins on one small blue world. Good night.